Okay, welcome to this lecture about spatial operations part 3, where we will talk about geoprocessing in a GIS. Let's see how that works and what the computer will need to do in order to get you your results. Geoprocessing are very powerful spatial analysis to model, for instance, coexistence of objects, variables, and phenomena. And such operations are really important in environmental impact assessments. For example, we can analyze crop suitability, or we can analyze nutrient leakage, or climate change, and things like that. Then we will actually use multiple layers to see the coexistence of different features. Or variables, if we see it as variables. This lecture, I will talk about vector overlay operations, and also I will show you a little bit about the vector model builder, where you can set up different scenarios and run it as a model. I will also talk a little bit about raster overlay operations, even if you have not yet come into the raster part, and how modeling is done in the raster feature format then. So let's look at the vector overlay that actually is we can see it as different features with an overlay. So in this case, I will have points with some sort of measurements. In this case, in this example, it's different field measurements of pH in different positions in the landscape. So that's the point layer. And then I have a soil type layer that is then a polygon layer. And my aim is now to see if pH and soil type is related to each other. Then I would need to do a point on polygon overlay in order to get the soil type value into the point attributes. So how is it solved? In order to know if a point is actually inside a polygon, as you now should know and remember, is just built up by corner coordinates. So we can see that A is, yes, it's definitely inside the polygon, but the computer doesn't see it like this. This is just another coordinate pair, an X and Y coordinate, in relation to the other coordinate pairs that builds up all the polygons. So how does the GIS program actually solve this? We could think this is very simple, but it's quite advanced actually. And this is the same when you click somewhere in the map in order to get the identity tool and see what feature are actually there. So how is this solved in practice? Well, the coordinate of the point the program have, and also then the different coordinate pairs that builds up all the polygons. A straight line is then generated in the point, and like this one, and it will be in a random direction, and then it has to check if this line intersects with any of the lines that builds up the polygons, and then it will have to count the number of intersections with the polygon border. If the point is inside the polygon, the number of intersections or crossings with the border of the polygon will tell us if it's inside or if it's outside. If it's inside, the number of crossings will be uneven. We have, if the line is drawn in this direction, the program will only find one intersection point that's uneven. So that tells the program that the point is inside that polygon. Or if it goes in that direction, we will see that with 1, 2, 3 crossings, it's still an uneven number that tells the program. If it's on the other side, or if it's on the outside of the polygon and the line is drawn, it will be even. It will go in and it will go out of the polygon. And this is how it's actually solved, to see if the point is inside a polygon. We can understand that this is if we have many different polygons and many different points, this is quite a job to solve. Luckily, we don't have to do it. The computer will count it for us. So if we have a points on polygon and all the computer tells us if the point is inside or outside, it will now create a new point file for us from the overlay function. It will be a new point file with all the points again, the same that we had before, and the same pH attributes that we had before. But a field in the attribute table have now been added that is telling us in which polygon each point was located. In this case, it was soil type, but it could also be municipalities or something like that. Then we would know if the point is which municipality the point is located in. So the point on polygon comes in with points, and we have a polygon layer, and out after the operation, a new point file is created with exactly the same points and the attributes, and added to the attribute table is the polygon properties of the different polygons. And then we can do a line in polygon overlay. And the question could be maybe, what is the length of a river stream in the different municipalities? And you will be working with these types of things for exercise 6, actually. So I have a line feature here. It goes here. Here we have a node because it connects to another stream here. And here we have a polygon layer that tells us what municipality we have, the borders of the different municipalities here. So the line layer is then have an ID value for the different segments and some sort of length if that has been calculated. And then we have the polygon layer with IDs for the different polygons. And the operation needs to find the intersection points between the lines and the polygon borders, break the line feature at these intersections, and add all the attributes from the polygons to each of the line segments. How is this actually possible, and how is this solved in practice by the GIS program? So we can understand that the line layer would now have to be cut here, or at least broken, and a node put in there. And then we will have a new segment here to here. And then we will have a node at all the entering and exiting points through the polygon. The program will need to to calculate the equation of each of lines. So the line going from this polygon, no, sorry, from this coordinate pair to this coordinate pair does have an equation of the direction it goes. And this one will have another equation, and this line will have yet another equation. And in the equation for the straight line, it's called y equals a multiplied by x plus b. And a is then how much the y value is changing for every step of x. And b, if we set x to 0, this will be 0 in the formula, and y will be equal to b at x equals to 0, which is then the point where the line goes out at x equals to 0. It hits the border here. But it can, of course, go through to the negative side, but this is where x is 0. So we have a formula for each line structure between two coordinate pairs. And at this point, we have actually the stream coming in, and this is then symbolizing the municipalities and the borders of the municipality. It will have to find this intersection point. And by testing all the different line equations for different values, it will find the intersection point where the same y value is put out if we put in the same x value. So if x is put into both of these formulas or equations, the y value would be the same. And then when it has done that, it will have to test also, is the intersection point located within the line segment? So otherwise we may find an intersection point, but it's outside the segment. So one last question will be needed. Is it inside or is it outside the segment distance? Okay, so we can understand now that it's a quite advanced operation to find that. And the output result will then be many more different segments of the line. So it will be split up into segments now. So this segment belongs to one municipality. This segment belongs to another municipality. And probably there should be a point here as well, as we have a node here connecting these two segments. That's my error in this figure. And then this segment of the river belongs to one municipality, in this case, Hör. And then this final segment of the stream or river belongs to yet another municipality. So nodes are inserted at the intersection points, separating the line into new segments. That coincide with the part of the line that is located inside the polygon. So out comes, we had a line input and a polygon input. Out, the result from this overlay operation is then a new line vector that looks a bit different. New segment IDs have been created. I will go to this one first. The municipality, which polygon the line segment is located within. And then if we had a length, it may have updated the length, or it may not. It depends on the output format. If we put it into a geodatabase, So the result is put into a geodatabase, the length will be updated. If we only let it out as a shapefile outside a geodatabase, the length will not have been updated. We see here it's the same length. And then if I want, I can recalculate the geometry in order to get the correct length for the different segments. So that's how a line on polygon overlay works. Quite many steps, but the program will solve it quite quickly. And then we have polygon on polygon overlay. That's when we want to know, for instance, the area of a certain land use, in this case, forested area. How much forest area do we have in different municipalities? And that means we have one polygon layer that is administrative regions for the different municipalities. And I have another layer that then tells us what land use class we have at different coordinates or different spatial locations. So a polygon on polygon overlay. And it has to now again find the intersection points between these polygons. It will have to test all the directions of the lines that builds up the polygon, which then I say again are not lines, they are just coordinate pairs, as you remember, but we can see it as there is a line between two coordinate pairs, but there isn't really. So we don't only have coordinate pairs. It will have to find these intersection points and break and redo the polygon layer that is output. So the output polygon layer from this operation will contain more attributes or more records of the with the combination of, so we have one polygon part that is called A1 then, which is this one and also this one. That means it's forest and within Lund municipality. A2 is also within municipality, but it's not a forested area, so it's agriculture. And so like this, the program lets you get a result from this operation. New polygons are created that are then probably smaller than the ones before. Attributes from both input layers are added to the new polygons. It's computationally very intense to find all the intersection points. As you now understand, it will have to compare the equations of the imaginary line between two coordinate pairs. And area attributes may not be automatically updated, depends on data format. So always be critical when you see the result. Is the area has the area been updated or not? And look at, so it's always good to know what you can expect from an output layer. And that's why you need to understand how these operations work, because then you will be able to look at the resulting output layer and find what you want in that layer. Maybe you are now only interested in selecting out the forest of Lund municipality, for instance, and then it will only be one record. There are different vector overlay operations for us to use in a GIS. I've talked about intersection, which is one type of operation actually. It computes the geometric intersection of the input features. So always use the help when you work with GIS. look at the figures that are available and try to imagine how your result will look like by following this. Here we see the input layers are 2 polygon layers in this case. But the output is only the common area between them. So everything else has been cut off and been deleted in the result. It doesn't delete the input layers, of course, but the output layer will only give you the common area. The identity will then instead give you the input layer as the mask, and in this area you will see in the attribute table that they have both, they belong to both polygons, both the identity polygon and also the input polygon. And the union operation then gives us everything that is both the input and the sort of union layer. So we need to be able to understand how to search out what we really want to know in the output layer. This one will only have attributes from the second or the intersecting layer. This polygon here will have attributes from both input layers, and this one as well. And this part will only have attributes for the input layer. So those are the most important operations we do in a GIS, the different overlays in their different tool functions. I talked about also when I talked about buffer zones in part 2 about dissolve, and I just want to show you what dissolve actually does. We saw that was a way of getting rid of multiple polygons on top of each other from the buffer operation. You can have a look at it there. But another dissolve function works like this, that we have multiple polygons with an attribute value. And we can see it as this is then a region in southern Sweden. And these are, we can see them as different municipalities. And they have an ID value that tells which region or district belonging they have. So the number 6 ID value in the attribute table will then tell in what district they are. And by using a dissolve operation, the borders, we get a new output layer where the borders have been removed, and all these polygons have now been instead one polygon, one big polygon, based on a common attribute that they share. And this is a way to go from parish to municipality or something. So we use a dissolve operation. Now, many programs have, and especially ArcGIS Pro, have a vector model builder. So if you, the thing is, you should know what process you need to do and what operations you need to do in order to get the result you want. And often you get a question that, if you're working on something, you get how much area does different municipalities have, for instance, of a certain type of forest area or agriculture or something. Then you should be able to make a flow chart of what do I need to do in order to solve that question. So here, this is a model builder. So it lets you take in different layers, and then the operation between them. In this case, it's a join field here. So we put this one into this one, the attribute data field, and then we add some sort of operation here, and we do a dissolve. So here, no, sorry, this one is the output from this one, of course. And then we do an operation here, and the output will be this one. And then what goes out, and here we have the result of the different things I asked. So this is a way of in GIS that you can do sort of a model if you know which operations you need and which order they should be in. Then you have to have pretty much understanding of how things work, and then you can just run the model, and that one is kept in the GIS program. And what's good with that is that you can just go in and change something in that one. Maybe we have see that we have different uh, other nutrient data types. Then you can just update this table and then run the model again, and your results will be updated. So you don't have to do everything again. So that's a good uh, good part of a GIS program. Not all programs can handle this, of course. So that would be maybe the results from a complex model. Um, we haven't talked so much about raster data yet, but you've seen this one, I think, that this is the vector model, and we see different land use types. Here we have deciduous forest, here we have coniferous forest or pine forest and houses. But this can be represented in the raster form as well, where we have an ID number of that pixel that tells us that this is deciduous forests, and this cell have deciduous forests inside it. So we will come back to raster, but we can see that we can also multiply and do operations on raster data in order to get out a result. So for instance, if we have the tree type, so in this pixel, or cell, as we call it in GIS. In this cell, we have a tree type equals to 1, and that could be maybe oak. And we have another tree type that is have an ID 4, and that is maybe birch trees, and so on. And then we have another raster that is exactly the same extent as this one, the same position. And here we have the age of the trees, maybe when was it planted, or today's, the year today minus the year the trees were planted, then we get the age of the trees. And if we in some case have a raster layer with the, with the annual increase in biomass based on the tree type, for instance. Now I know it doesn't really fit this one, does it? It's a bit, these ones are a bit error, actually. So if we multiply the age of the trees raster with the annual increase in biomass, we would get out a result of available biomass in a region, for instance. So that's how we do overlay operations in the raster form. We use different mathematical operations to multiply things, or there are some other ways of finding the information. But more about that in a later stage. And that concludes actually the the lecture series of today. I will now stop recording.